Hello. Today we're going to talk about resting membrane potential. So this has a little bit to do with electricity. Well, not a little bit. It has all to do with electricity, but it's kind of weird for me to think about. The human body is electric. Like we have ions inside of us. Ions have charges, and that creates electrical charges. And our body is able to use those electrical charges to send messages. Like our whole nervous system pretty much works as a result of a difference in charges. Neurons are pretty special because they can change their electrical charge. Most cells, they have an electrical charge, but they can't change it. Neurons are the exception because they can change it to send a signal or an action potential. So we're going to try to understand like what creates the membrane potential, and then later we'll move on to how they can change it. So there's a little neuron. Membrane potential depends on two things: the difference in ion concentration between the inside and outside of a neuron, like whatever ions are in here are different. That intracellular concentration is different from the extracellular concentration. And why does that matter? Because we know that ions have a tendency to flow down their concentration gradient. So, like if there was a high concentration outside and a low concentration inside, that would cause ions to flow in. Another factor is that the membrane has different permeabilities for different ions. That basically means that there's some ions that can pass through the membrane really easily and some that are a little bit harder to pass through. And both of those factors combine to create a membrane potential, or a difference in electrical charge between the inside and outside of the neuron. Let's take a closer look at the ion concentrations. So here is our same neuron, but we're going to zoom in right there on the axon, and then like this is the cell membrane. So then right here is like inside the neuron, and then right here is outside the neuron. So let's look at the ion concentrations, and what do you notice? The sodium concentration happens to be higher outside the cell, while the potassium concentration is higher inside the cell. And then let's look at how they will flow. So here's our same neuron, but this time I've added an ion channel. That's a protein that allows ions to be able to pass through it. So take a minute and predict which way you think the ions would move through their channels. If you notice that there was a higher concentration of potassium inside, the potassium will flow out, good. And there's a higher concentration of sodium outside, so sodium will flow in. So we can kind of think of it in terms of like what the ion wants to do. Potassium naturally wants to flow out down its concentration gradient. Sodium naturally wants to flow in, which is down its concentration gradient. However, in reality, there are more potassium channels and fewer sodium channels, which makes the membrane more permeable to potassium. So even though we're talking about passive transport, like things are just diffusing down their concentration gradient, a neuron has more potassium channels, which makes the membrane more permeable to potassium. So basically, more potassium can flow out and less sodium can come in. Let's think about how this could be affecting its potential or its electrical charge. Sodium has a positive charge, so potassium has a positive charge. So as potassium leaves, the inside would become more negative. If a positive thing leaves, the inside's becoming more negative. Sodium, also positive, and it comes in. So when sodium comes in, it makes the inside a little bit less negative. So we can think potassium leaves, gets super negative, sodium comes back in, gets a little bit less negative. And we would predict these to keep moving until they reach equilibrium, and then they just are balanced and they move in and out equally in both directions. However, this is not what happens. something keeps the ions from being able to reach equilibrium, and that something is the sodium-potassium pump. So pump tells us it's active transport. That means it requires ATP energy. The sodium-potassium pump basically works in the opposite direction of the ions. So like remember how potassium naturally flows out? Well, the pump moves potassium in. And remember how sodium naturally flows in? Well, the pump moves sodium out. And it's always in this ratio. So for every 2 potassium ions that are moved in, 3 sodium ions are moved out. So then if we look at it all together, here's our ion channels where potassium flows out. Here's our sodium channel where sodium flows in. And then here's our sodium-potassium pump, which is forcing sodium out and forcing potassium back in. And the overall result of this is that there's always a higher concentration of potassium inside the cell, and there's always a higher concentration of sodium outside the cell. And the difference in those concentration gradients creates the membrane potential. So basically, the inside of the cell is always a little bit more negative than the outside. Because so much more potassium is leaving, the inside becomes negative. Here is kind of a simple way to represent that the inside of a neuron is negative relative to the outside of the neuron. And if we take a voltmeter and we measure the inside compared to the outside, we'll find that the difference is 70 millivolts. So resting membrane potential is around negative 70 millivolts. Anytime that we raise or lower that, we can send a signal. But that's going to be our next lesson. Please watch this video about the resting membrane potential. It just goes over everything I said. And please send me all your questions. Thank you.